Hello. Yes, we welcome you back again. This is PSSB, Physical Sciences Silver Bullet, and it's Richard behind the channel. So we are having this question today. We are still doing grade 11. It says consider the potential energy versus reaction coordinate graph below. That's the graph we are having. On this axis, we have the potential energy. We are having reaction coordinate here. And then the first question comes. It says, state whether the reaction is endothermic or exothermic. Okay. How do you tell whether the reaction is endothermic or exothermic? You tell by the levels of the reactants, which we call the potential energies. If the product is having a higher potential energy than the reactant, then the reaction is endothermic. So that's the case, and we say it's what? It's endothermic. So now comes another part, another question here. Give a reason for your answer in 2.1 above. We have already given the reason. What's the reason? The reason is that the potential energy of the products is higher than the potential energy of the reactants. So that is that. So let us look at the next question on the same system. Yes, then comes this question 2.1.3. It says calculate the activation energy of the reaction. So here you have to know some stuff. There's something important you have to know. First of all, activation energy is always positive. That must be known to you. And when the question comes like this one, the implication is that activation energy wanted is for the forward direction. If they want for the reverse, they would have to put it in the statement. Once it's just flat without any direction, then it's forward direction. So they want activation energy for the forward direction. And how do you take it? It is going to be the peak from where the activated complex is minus where the reactants are. So in other words, it's going to be 1800 minus 600. So that is that. So let's go to the next question and we see. So then comes this question. It says calculate the enthalpy change of the reaction. How do we do this? So here you have to know that enthalpy change is given by the potential energy of the product minus potential energy of the reactant. So when you check here, what is the potential energy of the product? It is 1200 kilojoules. And what is the potential energy of the reactant? It is 600. Where you get 600 kilojoules as the enthalpy change. So it's kilojoules per mole. Okay. That's what we have. Yeah, then comes this question, 2.1.5. It says, identify what the following points on the graph represent. Okay, first one is X. What does X represent? X represents reactant. Okay, it represents reactant. What does Y represent? Y represents product. What does P represent? P represents activated complex. And what does Q represent? Q represents activation energy of the reverse reaction. Okay, what does R represent? R represents activation energy of the reaction. No, here you have to know that when you say activation energy of the reaction, you mean activation energy of the forward reaction. So that's how we answer that one. And then next question comes. Yeah, then comes this question. It says, redraw the graph in your answer book and indicate the effect of addition of catalyst to the reaction. So that's the question. You're supposed to draw this one and then indicate. So the question is, what does the catalyst do and to the reaction, and how would you show it here? What the catalyst does is to lower the activation energy. So from this, then it can lower it to that level. And if that's our new activated complex, then it means that our new activation energy is going to be this one. So this is it. EA catalyzed. So that's what that's how we show the effect of a catalyst on the graph. We just lower the activated complex, and that's it. Yeah, then comes the closing question of this video. It says, using the graph drawn, explain why addition of catalyst increases the rate of reaction. So we have seen what a catalyst does. It lowers the activation energy. But the question is, how does that lead to the increase in the rate of reaction? The answer is that when the activation energy is lowered, the number of molecules with enough energy to react increases. And when the number of molecules with enough energy to react increases, the rate of reaction increases. So that's what happens. So that is that. So this is what happens. Lowering of activation energy increases the number of molecules, particles, atoms with enough energy to react. So the key word here is this one. The number of molecules with enough energy to react increases. So that's the reason, and we are closing the video. We thank you for being with us. We thank you for subscribing. If you have not yet subscribed, please do so. See you in the next video.